Hey guys, good morning. I'm gonna try and wing another one here. It's still pretty much the same, but we got some dynamic situations going on with the ISWA space rudder, which I'll get to in a moment. Here it is, 9:33 a.m. Eastern Daylight Time. I keep saying Eastern Standard Time, but I guess it's still daylight time. And I'll switch the clocks back till somewhere around the end of the month, near Halloween. But anyway, here we go. Got you on the latest. Goes 16 from the coloradostate.edu. The reason I select this one with the Ram B slider is because they have these special other satellite arrays attached or whatever, but this is the best one to see it in natural color. And then you just go down there and click 60 for them, get the most frames, and 15 minutes for the time step. And here it is, pretty much the same deal. This is on the GOES 16 East, so it's parked in a geostationary orbit, 22,236 to 41 miles, 241 miles above the Earth, or 238, somewhere in there, plus or minus 5 to 22,236 miles. It showed up about the same time as it has been since the 17th when I caught this. There it comes. See that light beam? I believe that's something, planet or some pretty large object reflecting that light. Now they have everything pixelated out here. You can't really see it as much on the GOES as you can when we do the Himawari 8 later in the day when I make the vid in the evening or the late afternoon. But I mean, I believe it's the sun simulator is making the reflection because, well, for one thing, it's smaller, so that it's going to be more focused return on the reflection than it would be from the normal sun. I'm sure the normal sun's reflecting on here as well, plus the beam's light coming back at you. And if you notice, we got the full moon now, and that's quite bright white, which that's picking up the reflection from the sun simulator. I never put that together before, but I mean, the moon's been bright for a while, almost too bright to look at, really, for the last couple of years. But anyway, here's the latest ISWA space weather run, last 300 frames. And I got it stopped here. These two are running together simultaneous. Yeah, they're synced pretty close. This is the electrons at the highest high energy electron count level. You can see here, look at these gaps behind the fake bow shock, or false, not fake bow shock, but it has to be a secondary bow shock the planet had to develop. See these red closed field lines? These black ones are polar field cap streamers. They usually just stream away from the planet and are buffeted by the solar wind coming from out here. There's the arrows, solar wind. But I mean, as of late, the last couple of years or so, or last year or so, I'm getting a lot of this backside pressure. You can see it there. And so that's what those lines indicate, is our magnetosphere bucking up and trying to hold it off. And as you can see here, we got the blacks and the purples still, which are super high energy electrons. And this whited out area, I would contend that that is highest energy electrons that this thing's not able to measure. So they might be coming in, well, anything above 4,000 keV or 4 MeV, and they're not showing up here. That's how high and energetic they are. Okay, that's enough of that. Let's get back to this. This is some crazy stuff here. So I'll just step it through. Well, we'll just pull it through. So you can see, watch these. So here's where the Ram B slider, the Himawari rather, is. It's parked somewhere in its geostationary synchronous orbit. And in one spot, just to film the west side of the planet, and then the GOES E16, which I showed you this morning, films the other side. They pretty much stay in the same spot. That's where the satellites go round and round. Some of them go round and round. Well, there's a ton of them up there. But anyway, these ones here, I believe, are the ones that are giving us these data in order to make these computer simulations. So that being said, and this is the Z cut. We're looking straight down on the planet. Pretend you're a drone above the Earth, looking straight down. These arrows indicate solar wind coming from the sun, the light side. These arrows should always be going this way, right to left. But as you can see, we got a lot of pressure coming in from the back side. This dark blue is all plasma, super high energy electron plasma energy. And when it builds up from time to time, as you can see, it's building up back here. Then the Earth will expel it, thankfully. But from these electron belts, you can see the planet's being surrounded by high energy and low energy electrons. There's other Folk radiation electron belts, but I just pulled up the lowest low energy one and the highest high energy one. So let's just watch this playthrough. We'll start at the beginning, 1641. There's really there's really no missing time in here, except for maybe a few seconds here and there. So this is yesterday on the 23rd, 1653. So you take 5 hours off, or 6 since it's daylight time. That one put us around 10:41 a.m. or 11:41 a.m. depending on my math accuracy. So you can watch these wind speed numbers. These are all being recorded by these satellites here, not by ACE, which I'm going to show you in a minute. So these are the wind speeds in and around the Earth behind the magnetopause. Not too crazy. I mean, we've seen them go up as high as 1342, I think it was, or 1382. One dude put a comment that he saw it go over 1400 on 9/11, September 11th. You can see all the plasma energy building up. Watch the arrows. We got a bunch of stuff coming back at us this way. But here's where it gets funky. Got this huge wave come in, and then look what it does. It just almost disappears instantly, the pressure. Then the magnetopause gets bowed way out because we still got some backside pressure, I guess. So it's bowing it way out here. And it almost disappears. No velocity. You could see that here, the pressure. It's back to almost equilibrium between the backside pressure from Nemesis and the solar wind pressure coming from this side. These ones are flipped compared to ISWA. So let me show you this again. So there it is. That's the event. Go back to 757. So let's watch it on here. Gets even weirder here. So there's 757. Look at that. 801. Magnetopause got knocked down. These are Earth's radii here. 3,959 miles. So say approximately 4,000 miles. Normally it's out here around the 10 spot. 10 Earth radii. That's the magnetopause, the bow shock. Where it's out here at around 11. And just picture this as a magnetosphere and the bow shock. Picture this as being a boat going through the water, pushing the water out in front of it. So all this energy being pushed out in front of it's like water. It's a bow shock. This is the magnetopause. This is the barrier that our planet throws up to protect us from the solar wind. So you can see it was out there by 11 Earth radii, which is 1 past normal. So that indicates backside pressure. Plus, I think the magnetosphere is getting weaker. And then watch what happens. 4 seconds later, it's down here around 7 or 8, 7.5, I'd say. So it jumped down 3.5 Earth radii in 4 seconds. Now what in the heck caused that? Nothing showing up here. Here's ACE last 24 hours. I just pulled that up to show you. Well, I always pull up ACE, but I pull up the Discover to compare, and Discover's still down apparently. It says during times of Discover data outage or problems, and they revert back to the NASA ACE spacecraft, which is the older one up there, parked at the L1 Lagrange point. I pulled the link up yesterday. The ACE went up in 1995, and the Discover went up there in July of 2016. So they're both parked up here near the L1 Lagrange point, which is a place where they can park spacecraft and it'll just stay in the same spot without having to expend too much fuel. It's 930,000 miles in front of the Earth. So Discover's down. It's been down for the last couple of days. Here we're seeing the gaps on ACE, or this, yeah, ACE, because this is Discover showing us ACE data. There's a gap there. It's only, there's the timestamp up top. So it's 2136 to, so it's less than an hour there, and I'm running out of time already. 142 to 139, so it's about an hour there. But anyway, the point I was going to make about, look at the space wind, their solar wind speed rather. Normally it's 400 to 700 kilometers per second, so it's low. And I'm showing you the time frame, 7:57. That's when that wave hit the Earth. So you maybe back it up a half hour or so, or an hour at the most, because it might be that how long it takes to get to the Earth. These things are parked out here at the L1 to give the Earth an early warning signal from what's coming from the sun. So there's nothing that would justify this huge hit, knocking it down 3.5 Earth radii. And then it's getting all crumpled up there. So there it is. It's out to 11, down to 7.5, and it gets all spaghetti looking. That's 4 seconds later. That's all in a period of 8 seconds. There's 12 seconds. Now it's back out to almost 12. So we got a whole bunch of backside pressure. Here it is real quick on this Y cut, which shows you the magnetosphere from a side view. So here's my hypothesis, and I shared this with you before. We had the gaps on ACE, which were like 8-9 hour gaps. Then they went away for on the 16th and 17th, which we can't see here anymore. And then went back to 8 or 9 hour gaps. Then they went away again in the last couple of days. So whatever it is, there was a big planet out there that finally passed ACE. And I said, well, once it passes ACE, it's going to start showing up on Discover. And sure enough, it's not showing up on Discover because they took Discover down. So that's my hypothesis. The big planet's interrupting Discover, and they took it down. So anyway, I'm running out of time already. God bless and peace, and I'm out.